Hi Year 10. This is the first in a series of 5 videos for the topic of multi-step experiments, which is a probability topic. In our first lesson, we're going to review all the probability that you've learnt so far. And that includes sample space, theoretical probability, the sum of all probabilities, complementary events, and experimental probability. So the sample space of an experiment is a list of all the possible outcomes, and we use curly brackets and list the outcomes separated by commas. So suppose we want to write the sample space if we're going to throw a 6-sided die. Well, this is what we write in curly brackets, all the possible outcomes. So we could get a 1, 2, 3, 4, 5, or 6, and we put commas in between them. So if we want to calculate the theoretical probability that an event E occurs, we use this formula. This is the notation. This means the probability that event E occurs. And it's a really easy formula. We write the number of ways E occurs on the numerator and the total number of possible outcomes on the denominator. You might even see it written like this. This is set notation. This means the number of elements in the set E divided by the number of elements in the set S. And the set S is the sample space. Here's our first example. One number is drawn randomly from the set of numbers 1, 2, 3, 4, 5, 6. Find the probability that it's a 6. So how many 6s are there? There's just the one out of a total of 6 numbers. So our probability is 1 over 6. Find the probability that it's an even number. So evens are 2, 4, and 6. So there's 3 possibilities. Again, out of a total of 6. So we can either write 3 over 6 or 1/2. Find the probability that it's a number less than 5. Less than 5 means not including 5. So it could be a 4, a 3, a 2, or a 1. 4 possibilities out of a total of 6. Our probability then is 4 over 6 or 2/3. Now a standard deck of playing cards contains 52 cards. And they're divided into 4 suits. We have the red suits, which are hearts and diamonds, and the black suits, which are clubs and spades. Now it's important that you have a basic understanding of the makeup of a standard deck of cards. Now each suit contains 13 cards, and you can see here the spades suit. It goes all the way from ace, which is instead of a 1, and it goes 2, 3, 4, 5, 6, 7, 8, 9, 10, and then has jack, queen, and king. The jack, queen, and king are called picture cards or face cards. Now you might be curious about the jokers because when you buy a pack of cards, you actually have 54 cards. There are 2 jokers included. But in probability, when we talk about the standard deck of cards, we don't include the jokers. Okay, let's try an example. Jasmine shuffles a standard deck of cards and draws 1 without looking. Find the probability that she draws the king of diamonds. All right, so we've got to think, how many kings of diamonds are there? There's only 1. The total number of cards is 52, so our probability is going to be 1 on 52. Find the probability she draws a red card. Now you can do 26 out of 52, or you can go straight to a half. Half of the deck are red. Find the probability she draws a picture card. Remember, that's jack, queen, king of all of the 4 suits. So 3 4s is 12. So we can write 12 on 52, or we can write 3 on 13. And then finally, a heart. So remember, that's a quarter of the deck. We can write 13 on 52, or a quarter. Now the sum of all probabilities in an experiment is always 1. Let's have a look at this example. Liam draws a card from a standard deck of cards and writes down its suit. Show that the sum of probabilities for this experiment is 1. So we're going to work out the probability that he draws a heart, a diamond, a club, and a spade, and then add up those probabilities. Now each of those suits accounts for a quarter of the deck. That's actually their probabilities. So they're all the same. Probability of a heart is a quarter, diamond is a quarter, spade is a quarter, and club is a quarter. Let's add those probabilities up. And we're going to get 1. Let's move on. The complement of an event E is that E does not occur. Here's an example. I throw an 8-sided die The sample space is the numbers 1, 2, 3, 4, 5, 6, 7, and 8. Let E be the event that I throw a number greater than 6. So greater than means not including, so it could be a 7 or an 8. So the set E will contain the numbers 7 and 8. Now the complement is going to be all the numbers except for 7 and 8. So this is how we denote it, E with a line on top, and it has elements 1, 2, 3, 4, 5, and 6. Here's an example. A card is picked from a standard deck. Find the probability that it is not the 2 of spades. There's only one 2 of spades, so the probability that we pick it is 1 out of 52. The probability that we don't pick the 2 of spades has to be every other card. So its probability is 51 out of 52. And see how I notated this? This means the probability that we don't pick the 2 of spades. You probably picked up in that previous example that the probability of an event and the probability of the complementary event must add to 1. Let's have a look at that same example. Let E be that we draw the 2 of clubs. Show that the probability of E and the probability of the complement of E add to 1. So there it is there, the probability that we draw the 2 of clubs plus the probability that we don't draw the 2 of clubs must be 1 over 52 plus 51 out of 52, which is, of course, 1. Now, sometimes we're given an example without any context, like this one. The probability of an event A is 0.2. We have no idea what the event A is, but we don't need to know. We're asked to find the probability of the complement of A. So remember that these two add up to 1. So what do you think is the probability of the complementary event occurring? It's going to be 1 take away 0.2, which of course is 0.8. Okay, let's have a look at a couple of problems. A card is drawn from a set of 26 alphabet cards. Find the probability that we draw an A. Well, how many A's are there? There's only one out of a total of 26. What about the probability that it's not an A? Well, that's every other letter. There are 25 of those, so it must be 25 out of 26. The probability that it's a vowel. How many vowels are there? A, E, I, O, U. There's 5. So 5 out of 26. And then finally, the probability that it's a consonant. That actually is the complementary event to this one. Or we could count the consonants. Probably easier to do it this way though. 26 take away 5 is 21. So 21 on 26. Okay, last thing for this lesson. Experimental probability is the probability that occurs from an experiment. Now it may or may not be equal to the theoretical probability. We use a very similar formula. Experimental probability is going to be equal to the number of favourable outcomes, so the number of times it happens, over the total number of trials. And in statistics, this is called relative frequency. Here's an example. Gina tosses a coin 400 times and records 227 heads. Find the experimental probabilities for throwing a head and a tail. So out of a total of 400 trials, she threw 227 heads. So our probability that she throws heads is 227 out of 400. Now tails is actually the complementary event to heads. So to figure out how many tails she threw, we just need to do 400 take away 227. So the probability of tails is 173 out of 400. Now the theoretical probability in this case is a half. So out of 400 trials, we'd be expecting 200 heads and 200 tails. So you can see in this case, the experimental probabilities and the theoretical probabilities don't match. But here's the thing. As the number of trials increases, the experimental probability approaches or gets closer to the theoretical probability. Have a look at this experiment. A die is tossed a number of times and the number of sixes thrown is recorded. Calculate the experimental probability in each case. This is actually an experiment that I conducted with my Year 10 class. We threw dice a number of times and recorded the sixes. So when there were 100 throws, there were 15 sixes. To calculate the experimental probability, we go 15 over 100. I'm going to times by 100 to make it a percent. So the experimental probability was 15%. Out of 200 throws, there were 31 sixes, which is 15.5%. When there were 500 throws, there were 80 sixes. That gave us 16%. Out of 1,000 throws, there were 164 sixes. Experimental probability, 16.4%. And then finally, out of 2,000 throws, there were 334 sixes, which is 16.7%. Have a look at these numbers. What's going on? They're slowly creeping up, aren't they? From 15% up to 16, up to 16.7. What's the theoretical probability? There's only 1/6 out of 6 possibilities, so that's 1/6. To turn that into a percentage, we times it by 100, so the theoretical probability is 16.667%. Can you see how this probability is approaching that? So as the number of trials increases, the experimental probability approaches the theoretical probability. So let's summarize that concept. There's two types of probability. There's theoretical probability, which is what happens in theory. If I toss a coin 6 times, I should get 3 heads. Then there's experimental probability. This is what happens in practice, in real life. If I toss a coin 6 times, I could get 0 heads, or 1 or 2 or 3 or 4 or 5 or 6. But the more times we conduct the experiment, the closer the experimental probability gets to the theoretical probability. Okay, that's it for this lesson. In our next lesson on this topic, we're going to look at compound events.